Hey, what's up, guys? Yeah, so just very short video about this. As the topic mentioned. So, in the quantum computing, right? Previously, I make a video. If you haven't seen it, you can check my video list. So basically, previously, I proved that this Graver's algorithm is optimal. Okay, so the Curie complexity is optimal, right? For example, right, it says a capital N is 2 to N. And no matter what kind of quantum algorithm that you have, you can only solve this in omega square root n if you only access to standard quantum computing. So it's BQP. Okay, and this is proved by for a guy called BBB4. And what I want to say is that this actually gives the oracle separation from MP to B from MP and BQP. Okay. So the reason is very simple. Okay. So let me just quickly remind. So the previous results about this Simon's problem give you the separation, the oracle separation from BQP and BUP, because you can prove that this, if you use A to be this Simon's problem's oracle, then the BQP can solve this by just log n queries, but BUP need exponential one. Okay. And so from this before that we can just do the same thing and prove the following. So we want to prove that this MP A is cannot different from BQP A. We want to prove that there is this oracle A. Okay, and due to this search problem, the optimality of this Graver search problem, that we can just pick A to be the computation of the oracle compute. So it's oracle computes any Boolean function. Also, A is the powerful oracle. Somebody just give you a Boolean function, and you can immediately compute this. Okay, so you can immediately compute F. Okay, then obviously that this. Okay, so the goal is to solve the task, right? The task is just to suppose there's a unit X, right? Suppose there's a unit X such that X belongs to 0, 1 to the n, such that f of X is 1, and then the goal is to find X. Okay, so in this task that this can be solved in MPA, right? So L, let's say this is L, right? L belongs to MPA, right? Because right, you can just the certificate, it's just X, right? Because in general, if your F is very large, maybe very hard to compute, maybe you need the exponential size of circuit. But in this case, since you have provided this oracle A, right? So you can just compute f of X using A. Okay, so oracle can just solve this problem. But in BQP, right, if you want to solve this by quantum computer, then by the optimality, right, so your Graver is to take omega of 2 to the n divided by 2 curies. Okay, so basically it's proof that, so in this task that if you want to find this X, that you need this to take this omega 2 to n divided by 2 curies. So which is not in the BQP today. Okay, and you can use the standard diagonalization technique to make this very, very rigorous. But in this video, I just want to say this. Okay, so now we have these two facts that I think is proved 30 years ago, which is not difficult. Okay, so we have BQPA different from BBA, and then we have MPA different from BQPA. And the most, I think the other two is I think one is 2000 and the one is 2020. So one can actually prove that the BQP can actually separate from MA. So Okay, because you can like if you try to like to strengthen these results, then you can enlarge this BBP to be the complexity class, which is larger than larger than BBP, right? So the natural standard natural candidate will be MA, and the most famous one, which is very difficult to prove, called using the idea called fluoration, can show that this BQPA is there's a problem that BQP separated BQP from the polynomial hierarchy. So this one is like the most famous one, which prove that give you evidence that even like BQP is larger. BQP is very large that contains some problem, which may not be in the polynomial hierarchy. Okay, so see you guys next videos.